professional development course on advanced nonlinear control systems. Today we are honored that we have with us Dr. Amir Iqbal Bhatti, the most renowned professor of control engineering in Pakistan, and he is the person who is actually the main resource behind IEEE Control System Society, working for the betterment of this society in Pakistan. And we are indebted to him for his valuable time today. I will start with the servomechanism problem and move on to applications, and that will be followed by the course conclusion. Hopefully, Principal 6 will be attending as well in the concluding session, and hopefully we'll be finishing this session by 4:45 p.m. Okay. As the name indicates, this problem actually refers to addressing the stabilization problem while also trying to track certain trajectories or references, and also disturbance rejection is achieved while this is done. So this problem is a simultaneous problem in which we are trying to track prescribed trajectories. Those could be constant signals, those could be time-varying signals, periodic, non-periodic, subharmonic, stuff like that. And we are also trying to reject the disturbances at the same time. So there will be one controller which will be responsible of doing this. And as I go forward, I will show you a picture which we just saw when we were talking about integral control in the past sessions. And that picture will be similar, like this one. Now this servo compensator could be simply an integral, and when we are not dealing with signals which are constant anymore, they are periodic or they are time varying in some way, then we'll have to have a servo compensator. The difference between a simple integral control and a servo compensator will be the nature of supporting equipment with it, supporting mechanism with it, right? And we'll be talking about it briefly as we after we define the problem. Now there are essentially three different possibilities to approach this problem. Number one, if I can regulate the system by dynamic inversion, that means I need to have a perfect knowledge of the model, and then I make an inversion of it, make a control based on that inversion, and apply it. I can simplify it a little bit because this is going to need perfect knowledge of the model. But then I can talk about adaptive regulation. That means anything which is changing in the system can be known by some adaptation. Parameters are there, so we are going to estimate them by adaptation, or we are going to give the information to the system by adaptation. So it can, but still in these both methods, we have to compute a lot of things, and we have a dependence on computing those models accurately in order to make sure that the regulation or the disturbance rejection or the tracking problem is solved. The third thing is, which we are going to focus today, is regulation. This is via internal model. Internal model theory or internal model approach says that we are going to enable the controller to know about the presence of the tracking signals or the disturbance signals a priori. Now we are not going to be able to know about those signals accurately, but we can have some information about them, like frequency content or the bond or the amplitude, expected amplitude, so that we can talk about cancelling them or tracking them. Now this problem has tremendous applications in control problem, like trajectory planning of robot manipulators, like guidance of tactic missiles towards a moving target, like attitude control of spacecraft subject to torque disturbances. Disturbance appear here, reference appear here, and weapon system pointing and firing disturbances. For example, we've already sent a signal to the weapon, and weapon is already doing, and now we are giving it another signal, and the ship or the platform, which is the air vehicle, is also subjected to disturbances because of roll, pitch, and yaw of the environment, stuff like that. So we have to cater for all those disturbances while also trying to do what we have to do, like tracking these signals exactly the way we want to. A simple controller will not be able to do that unless that controller has information about expected signals. Now, when we empower our controllers with those kind of information, that means we are going to add something to it. And that addition of something is called the giving of exogenous signals to this system. That means we will have an external system, or we have an extra system which will be able to generate those exogenous signals. Once those exogenous signals are given, now servo compensator is a controller which has that information, that what kind of exogenous signal system is going to be experiencing while in operation. And then controller together with a stabilizing controller, this total thing becomes a controller. Now servo compensator is only going to operate under those conditions when references are there or disturbances are there. Otherwise, the whole thing is about stabilization. So in the absence of any signals which are disturbance or the reference, there's nothing like this. It's just zero. And then only thing is that the signal goes here and it computes U and plant is stabilized. That's the standard practice we have been looking at. But now when we are going to face signals of variety, and these signals are not known to us, that's the whole idea. When these signals are not known to us, what we do, we make a simple model, or we make an exogenous system model, which then allows us to have some kind of information about these signals which the real system, physical system may experience. And then based on that information, the controller computes an extra signal which will deter those signals, and stabilization will be achieved together with the stabilizing controller. So we'll have equivalent control. It has two parts. One will be stabilizing as before. The other one will be only on or off, or will be used when you have some signals acting on our system. So that's here. Now exogenous signal may include constants, and maybe they include sinusoids or harmonics. Linear theory to address this kind of problem dates back to 1970s when Francis and Bonham worked on this. Then Davison also contributed in a significant way. There are numerous manuscripts which were published in IEEE transactions on control, automatic control, by these three gentlemen. And then Rook and Chen and Lin have contributed a lot to this linear version of the servo compensation theory. Nonlinear theory has its roots in Isidori's work, which was seminal work presented in 1990s. And one of the important papers, which was by Isidori and Byrnes, that was in 1990, which published in IEEE Transaction Automatic Control, followed by 1994 work of Khalil in Automatica, and then further Huang and Proscoli also added, and together all these work actually make a foundation, and today numerous researchers are working on this particular problem. Now servo compensator, or this compensator together, achieves robustness against parametric uncertainty that does not destroy stability. However, whenever we add information in this kind of block, it actually adds to the order of the system, as we have been seeing before. When we add more eigenvalues to the system, actually the system becomes bulky, and now our performance may deviate from a performance which was for a smaller system. So transient accuracy or transient performance may be affected. So there is a solution to it. You just switch on those things when these things are present. That is called a conditional servo compensator, right? Or you can just include a traditional servo compensator which never switches on, never switches on, but then you are going to resort. All this this problem tries to address is that for a reference to be tracked, I want steady state accuracy. So sometimes we have to maybe compromise on transient performance in those cases. Yes. Exogenous signal, I'm going to show you one thing, and that will be here. Okay. This is my exosystem. If you look at the equation, W dot equal to SW, now this system can generate variety of signals depending on what is S. Now if you look at S like this, S equal to 0, that means W dot equal to 0, that means W could be any signal, but it will be constant. Now I have no idea what that constant is, and that's the whole idea. I am not knowing what is the unknown signal acting on the system. But if I have W dot equal to 0 embedded in my controller, then controller is now ready to expect any unknown constant signal, and it will deter against it. And if there is a disturbance, it will deter against the disturbance, or it is a reference, it will try to take care of that reference by tracking it. Other signal is, other example of S is this, 0, omega 1 minus omega 1, 0, which is actually generating this kind of signal, S-sinusoid. And now I have flexibility, I can add things here, I can change things here. If I have to make a bigger exosystem, that means I am trying to follow or track a reference which is constant, but also rejecting a disturbance which is sinusoid. So I can make it a third order system in which the first variable 0, 0, 0, then 0, omega 1, 0, minus omega 1, 0, 0. So I have first signal which is constant, the other signal is sinusoid. So I can start building it up. And I add it with my compensator, so that compensator has information about it. And then in real scenarios, when those signals actually appear, compensator already has the management of those kind of things. They can be deter, or they can be taken care of. But then we have certain issues to deal with. Number one, let's consider the linear plant in this form. This is the disturbance signal coming in here, and this is my state equation in linear format. And my error, which I need to regulate, that is z minus z ref. That means I'm talking about one control variable here, or multiple of them, and my z is the control output, so I have to make sure that this z, which is the control output, goes to z reference, so I have to render e equal to 0. So this is change of variables in order to make sure that this problem, which is a tracking or regulation problem, has been converted into a stabilization problem by suitable change of variables. Now, task is to design a controller. Now, this could be a dynamic controller, this could be a static controller. Static controller, as we have been saying, f is equal to minus kx, that is static, because we know x and we just multiply with k1, k2, k3, we apply it as a feedback. Dynamic controller are those controllers which have some extra information. They are not memory-less function, they have some other functions involved. That means we have now information about something in a dynamic equation, and that equation, when gives me a variable, will be responsible for generating some control input, which will be then applied to the system. They are more fruitful in most of the cases, especially in these cases when we have to reject disturbance and track signals. Now I have to design a controller like that, such that the closed loop system under that control is asymptotically stable, and number two, E goes to 0. That means Z goes to Z ref, or control variable exactly tracks the signal which I am trying to track. So closed loop system under this control, this system under this U, which is given here by HC plus KY, is given here. And if I just forget about this one for a while, this W, the system is actually here. Now, if I want to make E0, that means this guy has to be Herbert's. So I have to make sure that by choosing K in a sufficient manner, in a best possible manner, I have to render the eigenvalues of this whole thing. So I have now three things to worry about. This H, K, F, G, because all these are appearing here. This is a dynamic controller. Had it been a static controller, it was just a K problem. So we can do that with a static controller as well. But then we have to have information about the trajectories in a different way. But for a dynamic controller, now the problem lies to finding F, G, H, K, and with the given information of A, B, and C, I can find out and I can make this J Herbert's, right? That's the whole problem. Okay, problem formulation is that I'm assuming that AB is stabilizable and AC is detectable. And the second assumption is that I can generate W signal by this kind of exosystems, right? Any questions here? Okay. The assumption 3 is that I can read the error from output. Sometimes output offers more, sometimes output offers less. So, but assumption is here that I can find out the error, because then I can actually make some effort on designing control. So let's look at the closed loop system. Closed loop system has three state variables, W dot, X dot, C dot, and E is my output. I want this E to go to 0. Now let us look at this equation. It has one matrix or vector, other vector, other vector. I can call it vectors, matrix, or 0. This problem can be solved by Sylvester equation. Sylvester equation says that if I have three unknown things, then I can find out the solution of this pi and c by using this equation. And this is one important block which actually helps us finding what are we trying to find here. We're trying to find here the values of these two variables, right? If I can find these two variables, which is in this case, how have been we solving this kind of problem? अगर ये वाला प्रॉब्लम आपके जहन में आता है अचानक, अगर मैं आपको ये पोस्ट करता हूँ प्रॉब्लम, तो अगर मैं आपसे ये कहता हूँ कि I want to design a control, that means I want to find this K matrix so that I can solve this particular equation. What would I do first? I would just go and make an attempt to finding the equilibrium point for this one, right? The steady state condition. For steady state conditions, I just make this 0 and this 0, right? So, but that was the case when I was going to an equilibrium point. If I'm trying to track something and I'm trying to reject something, then I'm not going to an equilibrium point. I'm going to some place which will be based on some x minus xss or c minus css, right? Now that thing is a steady state value of that particular variable. What I do, I just name it that value is a fixed value, because if it is 0, then c minus css is actually saying that c equal to css, and x minus xss is saying that x is equal to xs. So what I do, I try to solve that. And this is one mechanism. Using Sylvester equation, by knowledge of these three things, I can find it out. And that's what I'm trying to do now. I define the error. That error is x minus the final value or the steady state value. And in this manner, if I can show that this is equal to j times this one, so j was Herbert's, right? Because we chose the matrices in that manner to begin with. These all control f, g, h, k were found in the, or assumed to be known, assumed to be determinable, and we were able to show that j is Herbert's. Once j is Herbert's, then I can show that x tilde dot and e tilde dot will go to 0 exponentially, because we have chosen the eigenvalues there, and that means that x tilde and c tilde will go to 0 as t goes to infinity. That means I will render x to its steady state value and c to its steady state value. That means I have solved the regulation problem which was formulated the way it was. Now, geometric interpretation of this thing is that I need this equation to be solved, and that equation, when limit e goes to 0, that means when steady state conditions will be supplied, is equal to this equation. This is also coming from Sylvester equation solution from here, and without going into much details, I'm just trying to say that this equation together with this set of equations is going to give us the solution in this form. And these equations together are called the regulatory equations, which are coming here now. This set of equation is regulatory equation which have been determined from those matrices, and it involves the knowledge of controller K1, K2, G1, G2, and F and H matrices. I've just split K1, K2 to address some control variable and some only measured variable, stuff like that. Just I'm trying to make sure that I can make it simpler as much as possible. And the second equation we just saw here, 0 steady state error implies this equation which is coming here now. So this set of equation is now reformulated, and these are the regulatory equation. Now, the theory says that if you can solve these equations, you can design these controllers. And when you can design this controller, that means I can render my error to 0, because when I implement that j, it is Herbert's, because it has eigenvalues based on choice of all these K1, K2, G1, G2, F and H, which are solved from here. So simultaneous solving of this equation, this set of equation actually gives us. Let's look at the interpretation. Interpretation is here. I start from an initial condition, and my controller, which has now two parts. One is to deal with the stabilization, the other one to deal with the error, with the references or the disturbances acting on system, actually takes the initial condition from here and brings it in finite time to a manifold, which is the steady state condition of that particular state. And if I look at geometrically, it is here. And if I look at the traditional map, which we usually plot, is that from an initial condition, I actually bring it here. So this particular figure is exactly equivalent in our standard MATLAB block like this. So under the influence of that control, which we just designed, after solving those regulatory equations, I can reach here. Now this is a general problem. We just considered the integral problem before, where we were using one sigma dot or one integrator. Now this is going to take care of all those things in its whole. So that's one. So how we design that controller? The controller is going to be designed based on the knowledge of the controllable pair, phi and theta 1, and an observable pair, phi and gamma. And you can see here, this is in a controller canonical form, and this is my observer form. And the controller is going to look like this now. It has some L matrix, M matrix, N matrix, K matrix. I'll just rephrase the names. And then I need the knowledge of phi and theta 1 and C. These things depend on the knowledge of W, which is given to the system. So what happens when I feed it back? This block is coming from this point. Over here, I add something, and then I compute this whole thing, and then I create U. So have a look. I compute Y, it goes here, then I compute U prime and U double prime, it goes as U to the system. This is servo compensator. If there is no error, this will vanish. Only stabilization is required. If there is error, this will play its part and U prime will be given. So if there is no disturbance, no reference to track, no disturbance to reject, it's just a stabilization problem. If there is something which is that means Z is not going to ZREF, that means there is some E value. So this will be there and it will render it to 0 in that case. So controller design is going to be now based on FG1 and this systematic way, solve this equation, solve the regulatory equations, and we can then show that solving that equation will actually mean that this particular thing will boil down to this requirement, and once this requirement is met, that means E goes to 0 as time goes to infinity. And similarly, we can use this same idea for stabilization of that system, and the requirement is that the pair, which is given here, A0 theta 1 C1 phi, B0, is stabilizable, and this pair, which is A, B, and lambda 0 phi, C0 is detectable, which is all coming from all these things, and this particular equation is actually solved by solving this particular equation. That's the regulatory equation. Okay, that was linear part. In nonlinear servo mechanisms, unfortunately, we don't have ABCs, but we have these functions. Now, if we assume these functions are Lipschitz and continuously differentiable, but there is another problem. When I say that I am going to use an exosystem which is linear, in the past case we just saw that the exosystem was a linear exosystem to begin with, right? In nonlinear systems, we might have to go with an exosystem which is nonlinear. But in our presentation today, I'll just restrict ourselves to linear servo mechanism because nonlinear servo mechanism actually creates a problem. I've just given some remark here. If I just say I'm going to stick with W dot equal to S capital S matrix times W, and I solve the problem, now I have to have a manifold. That means I need to have a steady state surface if I am talking about second order system, manifold if I am talking about more higher order systems. Then I need to show that number one, that manifold, which is the steady state condition, is invariant, because I have to eventually reach somewhere. If I have to reach somewhere, I have to make sure that it is invariant to the atmosphere, the environment. And then I need to know the steady state solution of my state. So I go here and I do the same thing. I make 0, 0, and I try to find out the steady state conditions. And the steady state conditions are solved here. Let me go back in a minute and I'll try to see. Okay, these are the steady state conditions and pi and sigma are the steady state values of my respective variables. Okay? Okay. Now task is to design a controller of this form which will render the state x and c bounded and error to 0. And the closed loop system under that controller is now given here. Now just remember, we are trying to do the same thing here as well. We are trying to see that I have a J matrix of some form. When I can assign eigenvalues in linear case to make it Hurwitz, I will try to do something similar here, but we do not want to go to linearization in this case because that will be a local analysis. We want to make it a little bit regional. So in that case, what I do, I try to find out the steady state manifold, and that is here. Now suppose that J which we formulated here, which is now the gradient of my function f and function phi with respect to its respective variables, I say that this particular thing has a steady state solution, and that steady state solution is here. I assume that x goes to pi eventually and c goes to sigma. Now what will be my problem? I will have to define error variable. Error variable will be x minus pi, and the other one will be c minus sigma. So I have to make sure that I reach there. What I do, I solve the regulatory equations, and again I need some condition. The previous condition was c1 pi plus q1 was 0, which was rendering E3 0. Now I have a similar condition here, which says that h pi, which is my output, is 0, and that renders that E equals to 0. Now from here, I can just try to give you some geometric interpretation here. I have this initial condition. My controller brings this particular initial state, set of initial state, by use of a control, and it tries to render it and bring it to a manifold. Remember, we are not talking about stabilization on an equilibrium, because in this case, we have no idea what is the reference and what is the disturbance, because they are unknown disturbances, unknown references, so we have no idea what is equilibrium to begin with. We have only one knowledge, that if I make x minus pi equal to 0 and sigma minus c equal to 0, or the otherwise, that means I'm going to actually regulate my thing where it is supposed to be, and that regulating thing is actually changing because disturbances and the references are changing all the time. Okay? So that is the thing. So this, I have no idea. I only know that this is some steady state value. My controller is now responsible to bring the initial state from here and render it on that manifold. For this, I solve the nonlinear partial differential equations, and then I introduce the exosystem in there. Okay, and there is a systematic way of designing control, but in this systematic way, we have to solve an equation. The Isidori calls it that there are certain variables immersed in it. So we have to solve the immersion condition, and then we find a servo compensator of this kind. In this case, stabilizing compensator could be sliding mode controller, could be Lypunov redesign, could be any other. Servo compensator is straightforward, the similar way as we did it before, but here one thing is extra. In nonlinear systems, there could be harmonic distortions of harmonic variants of the signals. Okay, for example, if you look at a pendulum equation, it may have some cubic term as well. Now when you apply a signal which has a cubic term, then when you go and analyze that cubic term signal, it will have components which may be in fundamental frequency but also in third harmonic. So my controller here is also to deal with a third harmonic as well. So we have to empower that one in that way. So here, the servo compensator may have to address those harmonic issues as well when we are subjected to certain signal of certain frequency. That's why we need to have knowledge of the expected frequency in order to make sure that I can handle those harmonics as well. Now let me give you a couple of examples so that you can understand. I know it has been too much for you to digest in a small session, but I just wanted to introduce this thing so that you can read about it in the literature. I can point you some papers. You can read about it because this is one of the fundamental problems these days. Okay, if I start from here, inside a set, and my initial conditions are such that they just go away and there's no control, u equal to 0 at this moment. I'm not applying any servo control, I'm not applying any stabilizing control. So if they go away because of the disturbances or whatsoever, that means I am going like that. So it is an unstable system to begin with. In this whole argument we have discussed today, we have to find out this one and we have to find out the manifold here to begin with, to sort out the issues. Now, if I have found out the steady state manifold and I have only applied the control, which is the servo control, not the stabilizing one, initial conditions start right on the manifold, that means the servo control is going to be able to do it and everything will be nice. It will remain there all the time because servo control, which is because I am having some disturbance or I am tracking some reference. So servo control is going to be enough to make it. I do not need the stabilizing component because nothing is going out. It is already there. But this is pointing to that thing. If I have to stabilize pendulum at delta, I need to have some control to put it there. Otherwise, when I leave the control, it will go down. As soon as I leave control here, it will be like this. If I apply the requisite control to maintain the trajectory over there, that means I keep on tracking the references and rejecting the disturbances, then I'm here. Now, if I'm far away and I have to reach the manifold, it could be a sliding mode control problem in the end. But I have to start from somewhere, I have to stabilize it, bring it to that manifold, and then I have to maintain it. So my controller in the beginning is going to be a stabilizing component, which is bringing it there till the time it reaches here, and then maybe this will switch off and this will remain because it has to maintain it. That means I am taking from some initial condition, going and I am stabilizing, and on that condition my error is 0. My control variable has been stabilized. Okay, this was all which I actually planned. Now I'm talking about some applications just to give you some idea, and I will be a little bit I'll be going with the pace because I have to meet some time constraints. Presenting now the things which will actually allow me to introduce you few things which I have worked myself, so that you can understand how we can implement these things. This is one of the old works I had done in my master's, and later I pursued a little bit further on it. That's why the you can see the background is like very old. Okay, as the topic indicates, it's a speed control, central speed control of induction motor using sliding mode control. Since we talked about sliding mode control a while back, so I will just introduce you what I am trying to do here and try to compare the performances of a couple of mechanisms. I'm just ignoring the requirement of induction motor drives, I know. One thing to understand this problem is the Park and Clark transformations. We can transfer three-phase thing into two-phase things by DQ transformations. And this is the matrix which actually is responsible for changing between reference frames. Speed control in induction machine is achieved by various means. One is voltage flux, voltage hertz methods and stuff like that. So these are constant voltage per hertz, constant slip speed, and vector control or field, FOC, field-oriented control. Our work will talk about field-oriented control, and that means I can transform these signals from A, B, C to Q and D and stator frame. Okay, two things are important to understand here. One is that the flux, rotor flux, can be made proportional to the current, field current. The other one is the torque can be made equal to one of the currents or the coupling term of the currents, right? Okay, let's see what happens now. Induction motor model is here. To reach a desired